Throughout history, the common net has played an essential part in the daily life of man. As with any textile structure, the making of a net has traditionally involved a number of quite separate processes. This is true no longer, for there now exists a unique technology which takes a raw material and transforms it into a mesh structure in one single and continuous process. This is the Netlon technology, so versatile that in looking at its applications, we shall leave far behind the conventional uses of the net. Dr. Brian Mercer, an English textile technologist, invented the process for the production of this extruded plastic mesh during his research into textile structures, and he called it Netlon. Although the process has developed considerably since then, the basic principle remains the same. The process begins when a thermoplastic resin is introduced into a conventional screw extruder. A small percentage of pigment is sufficient to give the product its required color. The resin is forced along the barrel of the extruder at increasing pressure and temperature until it enters the Netlon die head. It is here that the mesh structure is formed. The extruded mesh is then passed over a mandrel and through a cooling tank before being subjected to any further treatment which may be required. Orientation, or stretching, is the most common, and it's carried out as part of the continuous process, using further Netlon technology. These are granules of polymer. Most thermoplastic materials capable of screw extrusion can be used in the Netlon process, and such additives as rodent deterrents, anti-static agents, and flame repellents can be included. What precisely happens in the Netlon die head to change a stream of molten plastic into an intricate mesh structure? Mounted on the die head are two counter-rotating die lips, into each of which is cut a series of slots. It's through these slots that the polymer is extruded, and it is their relative movement which forms the mesh structure. What happens when one of the dies is made to rotate? Each stream of polymer is divided into two. As the rotation continues, the next slot in the inner die comes into register with the slot in the outer die. This slot has carried with it a stream of extruded polymer, and the two streams are united. When the two dies are stationary, the extruded polymer forms continuous machine direction strands. Let us watch the Netlon process when only one of the dies is rotated. We can see that as the slots momentarily come into register, the strands converge to make the intersections. And when they move out of register, the interconnecting strands of the mesh are formed. The mesh structure can be changed simply by altering the movement of the dies. This is what happens when they are counter-rotated. Now let's look at what happens when one die is held stationary while the other is oscillated. It's also possible to oscillate both the dies. Because the dies are circular, Netlon is always extruded in this tubular form. But it can, of course, be split to make flat sheets where this is required. The basic form of Netlon is this diamond mesh structure, made by counter-rotating the dies, and it has a large number of applications even in its tubular and non-oriented form. In the vast forests of the northwest region of the United States, foresters fight a continual battle against damage done to seedling trees by such animals as the porcupine, the bear, the mountain beaver, and most particularly the black-tailed deer. By far the most successful method of combating this damage is by the use of Netlon tubes, which fit around the seedling trees, protecting the important lead tendril for the first 3 to 4 years of the tree's life. Ultraviolet light degrades different colors of Netlon at differing rates, and these tubes are made in this special pale color in order that they may break down once the tree is safe from the browsing animals. The use of Netlon reduced losses by 50% over all other methods of protection. And the fact that the lead tendril is partly in the shadow of the tube means that the tree grows 15% faster in its efforts to climb up to the direct sunlight. Another use of the Netlon tubular diamond mesh is found here, on the Japanese island of Kyushu. The East China Sea has been eroding the land for thousands of years. But that is now prevented by the use of these gabions, rock-filled tubes of Netlon, sealed at each end and held in place by piles driven down into the earth. Seawater would corrode steel, but these high-density polyethylene tubes will last indefinitely and have the added advantage of being easily handled and transported. In a paddy field in another part of Japan, Netlon tubes are being laid as drainage pipes. The drainage system in a paddy field cannot make use of sand or crushed stones as a filtering layer around the pipes, and so they must be laid directly into the earth. This Netlon pipe combines rigidity with mesh apertures small enough to provide adequate filtration. Better drainage allows for the use of heavy agricultural machinery, when this was not possible before. Around the coast of France, there are huge oyster beds covering many hectares of intertidal water and containing millions of oysters. The vast majority of these oysters are now raised in Netlon pockets, which prevent them from being scattered by the tide and make them considerably easier to handle. Each pocket contains up to 30 kilograms of adult oysters and can be used many times. Again, this is a tubular diamond mesh structure. But this time it has been cut into sections, which are closed at each end. They're fixed to iron supports, and at high tide they become totally submerged. We've looked at some applications for the basic tubular cast net. Now let's look further into the Netlon process itself. At the very heart of the process are the Netlon die lips. The characteristics of any particular mesh are dictated largely by the shape and the spacing of the slots cut in these die lips. The speed at which they rotate and the nature of their movement will also influence the mesh pattern. The cross-sectional shape of the die slots can be changed according to the product required, and numerous shapes are employed, all having their own advantages. The highest degree of precision engineering is exercised when cutting the die lips. Once the work has been correctly set up and the electronic numerical controls programmed, slotting and indexing are carried out automatically. After cutting, the dies may be hardened through heat treatment, and in some cases their surfaces are chemically treated in order to give further abrasion resistance, ensuring that finished products will be of a consistently high standard. We shall now look at the first of the many treatments to which the tubular cast mesh may be subjected: the slitting of the mesh for use in sheet form. This is done quite simply by drawing the extruded mesh over a cutter as part of the continuous process. The British Gas Corporation developed a use for flat sheets of a Netlon cast diamond mesh in the cathodic protection of steel pipes carrying highly combustible natural gas. Originally, these pipes were surrounded by a collar of sand 10 centimetres thick before the trenches could be filled in. But in many cases, the nature of the terrain made it uneconomical to transport sand to the sites, and so a replacement had to be found. The pipes are now wrapped around with this heavy-duty Netlon structure, which allows fine particles of earth to percolate to the pipe's bitumen coating, whilst preventing abrasion of the coating by rocks or stones.
Okay, away you go.
Behind this oil refinery, at Yokkaichi in Japan, 60,000 square meters of marshland are being prepared for the building of an industrial complex. A Netlon cast mesh in sheet form is being used as a restraint layer. Very little preparation of the land is needed before the Netlon can be laid down and the sheets sewn together. Work can begin immediately, covering the Netlon and laying the foundations for what will eventually be an area of factories and warehouses. This is a common application for Netlon in Japan, where it is used in many areas of civil engineering, for example, in the construction of the new Tokyo International Airport. A third use for flat pieces of Netlon cast mesh can be found in the Japanese prefecture of Nagasaki. These trays are made from pieces of Netlon nailed to a wooden frame, and they are used for drying fish, both in sunlight and in artificial conditions. Here, Netlon has a number of advantages over other materials in that it does not stretch or sag and is easily cleaned. Furthermore, since it's not a fibrous material, the fish do not stick to the mesh. So far, we've seen applications for Netlon in which the mesh structures have a diamond shape. But there are some applications for which a square mesh structure is better suited, and Netlon have their own way of producing this. A diamond mesh with angles of 90 degrees is made by holding one die stationary whilst rotating the other. As this mesh is drawn down the mandrel, it is made to rotate, and a cutter is set against the mandrel in such a position that it will slip the mesh helically between a pair of adjacent strands. The rotation of the mesh is caused by the haul-off tension of the split sheet, as it passes under a roller set at 45 degrees to the mandrel. By this method, a continuous sheet of square mesh structure is produced. 35 million square meters of square mesh Netlon are sold in Greece each year for use in the harvesting of olives. The nets are 5 meters wide and are spread over the entire olive groves in early November when the harvesting begins. The Netlon ensures that air circulates under the olives, keeping them dry and free from mildew. Where olives are allowed to fall directly into the grass, many are lost and others decay. The system is used extensively in other Mediterranean countries and can reduce harvesting labor requirements by as much as 90%. For this purpose, a structure is needed which is both flexible and lightweight. This type of structure is made by stretching the strands of the mesh. In the case of square mesh structures, this is done in two directions. The first, longitudinal stretching, is done on a machine consisting of a series of rollers, which carry the cast mesh at a progressively increasing speed through a hot water tank. This machine-directionally stretched mesh is then fed to a second machine, which by gripping the edges of the mesh and conveying them along divergent paths, stretches the transverse strands. The machine consists of two wheels revolving together and set at an angle dictated by the degree of orientation required. The edges of the mesh are taken up at the narrowest point, and as the wheels rotate and diverge, the mesh is transversely stretched. The machine is shown here operating slowly in order that the principle may be clearly seen. In commercial use, speeds of up to 100 linear meters per minute are achieved. The effect of this stretching is not only to increase the mesh area, but also to greatly improve its strength through the orientation of the molecules within the polymer. This form of biaxially oriented mesh has a variety of applications in addition to the harvesting of olives. Here in Orange County, California, as in other parts of North America, the use of Netlon is revolutionizing the commercial growing of turf. Shortly after the seed is sown, this square mesh Netlon is laid down from rolls 3 meters wide and 1,000 meters long. Then follows a period of watering, fertilizing and mowing, which, together with the effects of the California sun, bring the turf to readiness for harvesting in 1/3 of the time usually required. Normally, the grass must remain in the earth for 1 year before the root system is sufficiently intertwined for the turf to be harvested. Furthermore, the soil must be cut to a depth of 2 centimeters. Whereas with the Netlon mesh reinforcing the root system, it's possible to harvest after 4 months, whilst cutting to a depth of only 1¼ centimeters. The mesh used here is an oriented square mesh structure, but it is also possible to orientate diamond mesh structures, and they have a number of applications. In this German vineyard, a diamond-oriented Netlon structure is used to prevent birds from spoiling the high-quality grapes. A square mesh structure would not drape itself around the vines in the necessary way. The same mesh is also used to protect such high-value crops as strawberries and raspberries. These diamond mesh structures are oriented in tubular form by being passed over a series of rollers rotating at differential speeds and through a hot water tank. This stretches both sets of strands at the same time. For the protection of grapes, this mesh is slit, but it has a number of uses in its tubular form. For example, packaging in Spain. shortage of labour has created an increasingly important role for fully automatic packaging machines, and the Netlon organisation has contributed towards the development of such machinery. In addition to its use in packaging systems, Netlon fulfills another important role in the manufacture of bags, made from an oriented diamond structure simply by cutting the tubular mesh into sections and sealing or sewing them at one end. Suitable for weights up to 25 kilos, bags such as these are used for packaging such diverse items as fruit and vegetables, toys, shellfish, and bakery products. There are some applications for which a diamond mesh structure with a degree of stability in the machine direction is required. This is best achieved by the use of a mesh structure made up of 3 strands. A 3-strand mesh is made simply by separating the 2 rotating dies and inserting between them a 3rd stationary die. The slots cut in this die will extrude the stabilizing machine direction strands, whilst the 2 counter-rotating dies extrude the diamond mesh in the normal way. These tray covers are made from a 3-strand mesh, and it's also used for insect screening. In all the applications we've seen so far, the strands forming the mesh have been of equal cross-sectional shape. But with the Netlon process, this need not be the case. This is what is called a tartan mesh, produced from counter-rotating dies cut with slots of an irregular cross-sectional shape. Drifting snow is an annual problem during northern European winters, when snow tends to form drifts around hedges and perimeter fencing, frequently blocking roads and railways. To keep as much snow as possible away from these barriers and gather it where it will do no harm, snow fencing is erected at the beginning of each winter. This Netlon structure, with its wide strands and large mesh apertures, is ideal for this purpose, since it causes a broad drift to form, absorbing a large quantity of snow. Furthermore, since it must frequently be erected on farmland, the ease with which a Netlon fence can be put up and taken down gives it a great advantage over conventional wooden fencing. The system has proved so successful that Netlon is now widely used as snow fencing in northern and eastern Europe. It has a further advantage in that since the plastic does not interfere with radar scanning, it's ideal for use at airports, both as perimeter fencing and as snow fencing placed directly alongside the runways. In creating a structure to control soil erosion, 4 layers of Netlon mesh are bonded together at regular intervals and then heated. The bottom layers of oriented mesh contract, whilst the top, non-oriented layers do not, creating this 3-dimensional structure. In the lowlands of eastern England, winter flooding can be a serious problem. Netlon erosion control mat is being installed on this flood prevention bank in Lincolnshire. Available in widths of up to 4.5 meters, the easily handled mat is secured to the slope with steel pins. The upper surface of the mat is a network of pockets which will retain the layer of soil, whilst its flat back allows it to follow the contours of the ground. Once covered, the mat protects the slope against erosion caused by wind, rain, and sudden flooding. As grass becomes established on the bank, the mat will reinforce the grass root network, providing further erosion resistance. Finally, in the Netlon Research Laboratory, infrared thermography is used to study the thermal condition of mesh products as they're produced. Computerized analysis using videotape recordings of these images enables the Netlon engineers to study such details as process zone temperatures and specific cooling profiles.
Through this continuous research program, process improvements and new polymer mesh structures are being introduced to meet new market needs. It is only through this work that the full potential of the Netlon process will be achieved.
The infinite variety of mesh structures which the Netlon process can make play an essential part in the daily life of man. But as the technology spreads to new territories, the demands made upon it will increase, and it will undoubtedly fulfill many uses which are yet unknown.